Okay, we're going to look at today at binomial coefficients. Now, last time we looked at binomial expansion. So we looked at something of the form a plus b, and if we want to expand it to the power of n, where n is a positive integer. Now, if n's large, we went through Pascal's triangle, and it is easy to see that quickly the numbers are going to get really big. So for here, if n's 5, this is going to be this part of the triangle. The coefficients for this expansion will be this line of the triangle. But what if we wanted to raise it to the power 9 or 10? You're going to have some really big numbers, and working out these the coefficients of the expansion using Pascal's triangle isn't always that practical. Now, we call the coefficients in the binomial expansion binomial coefficients. Now let's consider 1 plus x raised to the power 5. Well, that's going to be 1 plus 5x plus 10x squared plus 10x plus 5. Oh, wait a minute. How is it? X cubed, sorry. Plus 5x to the power 4 plus 5x to the power 5. And you can see these are the coefficients here. Now, what we're going to do is we can actually calculate these coefficients by using the calculator. So if you look on your calculator for a button which looks like this, NCR, or it might look like NR. This can allow us to work out the coefficients. So if we can think of each of these coefficients as the top number is 5 because we're raising it to the power 5, and this one is 0 because the x, I think x is to the power 0 here, so that's where we get the 0. The next one is 5, and that x is to the power 1, so that's 1. And then it'd be 5 to the power 2, and then 5, 3, 5, 4, and then 5, 5. So if you can find whichever one of the buttons is on your calculator, and if you put in, let's say you did it for this one here, if you were to type 5, then use the NCR button, it's N choose R, and then hit hit number 2, you will get 10. And so we can think of, if we have an expansion of 1 plus x to the power n, then that becomes n to the 0 plus n to the 1 x plus n to 2 x squared plus all the way up to plus n to the n x to the power n. This is known as binomial theorem. And we can, if we can also write, if we can expand it for the general a plus b, which I'll write that on a new sheet. So we can have a plus b to the power n can also be written as a to the power n 1 plus b over a to the power n, assuming that a is not equal to 0. And then we get the general rule of a plus b to the power n is going to be n to the power 0 a to the power n plus n to the power 1 a to the n minus 1 b to the 1 plus n to the power 2 a n to the n minus 2 b to the power 2 plus all the way up until you get to the final one, n to the n b to the power n, which is the same idea as what we had for our generalization previously. So this is our binomial theorem. Now we're going to look at how this works in practice. So we're going to find in ascending order, in ascending powers of x, the first 4 terms of the expansions. Firstly, we're going to do 1 plus x to the power 15. So 1 plus x to the power 15. Now remember, we only want to find the first 4 terms. So the first term is going to be, so the n is 15, and it's 0. And a here is 1, so we don't have, that would just be 1. Then plus 15 to the 1, 15, 1, and then a is still just 1, so then, but it's going to be b, which is x raised to the power 1, plus 15, 2, and then it's going to be x squared, then plus 15, 3, and then it's x 3 plus, now although it's to the power 3, we started at x to the power 0, so we didn't have, that's our 4 terms, 1, 2, 3, 4. Now, for these, use your calculator to find out what n choose r would be. And you'll find 1 would be 1 plus 15x plus 105x squared plus 155x cubed. That's whatever that would be. Next we're going to do 2 minus 3x to the power 10. So just draw a line under there to separate them. Power 10. So we've got, our first one is going to be 10, 0, and now this time we've got, if we think about a plus b here, a is now 2. So we're going to have 2 and it's to the power 10. And then we've got b, and b would just be 1. Then 10, 1, so then we've got 2 to the power 9. And then we've got minus 3x, now remember it's minus 3x, and that's going to be raised to the power 1. and then we've got 2, and then we've got 2 to the power 8, then minus 3x squared, and then we want one more, got 10, 3, 2 to the power 7, and minus 3x to the power 3, and then plus whatever. It's going to continue. We're not going up to 10. So now, using your calculator, you can work out these. So we're going to have 2 to the power 10, and that would be 10 choose 0 is just going to be 1. That's going to be 1024, because it's 2 to the power 10, plus, working out all of this, it's actually going to be minus, because this is where you have to be careful. This minus 3 gets raised to the power 1, so it's going to be minus 3. It doesn't cancel. So it'll be minus 15,360x. Then this minus will be cancelled into a positive, because minus 3 times minus 3 is going to be 9. Oops. So we're going to end up with 103,680x squared, and then minus again 414,720x cubed. So all of this just gets plugged into your calculator, and that's our first 4 terms. It should be noted that whenever you have n to the power 0 and n choose 0 or n choose n, they both equal 1, which would make sense, because when you've got Pascal's triangle, all the outer numbers are all 1, regardless of what power you go up to. Let's consider, let's look at these numbers: 5, 1, 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4. So this means 5 over 1, which is 5. And this is 5 times 4 over 2 times 1, which is 10. And this is 5 times 5 times 3 over 3 times 2 times 1, which is also 10. And then this is 5 times 4 times 3 times 2 over 4 times 3 times 2 times 1, which is equal to 5. And these are just little tricks that you find in Pascal's triangle. But as you can see, if you look at the top number, it's 5, 4, look on this one, 5, 4, 3, 2, 4, 3, 2, 1. We can see there's a pattern here. And what we find is, in general, for n choose r is n times n minus 1 times n minus 2 times all the way down to n minus r plus 1. And then you've got r minus 1 times r minus 2 times r minus 3 all the way down to 3, 2, 1. So we can use this for in an example. So when 1 minus x over 3 to the power n is expanded and extending hours of x, the coefficient of x squared is 4. Given n is a positive integer, find n. Now, so let's think about the term in x squared. So, for x squared we'd have n, choose 2, and we're looking at this part of it, so that's 1. We'd have minus x over 3 squared, and that would give us n times n minus 1 over 2 times 1 times, now this is, the minus is going to be, lose the minus, minus and minus is positive, and that's going to be 2 squared, 3 squared is 9, and then we will have, that'll be 2 times 9 is 18, so n times n minus 1, in brackets, x squared equals 18. Now, we know the coefficient is 4, so we're going to, this is the coefficient, so let's take this here. But n times n minus 1 is 72. So let's expand this out. Minus n, we're going to bring this over here, so we get a quadratic equation equals 0. And now we're going to solve the quadratic equation. So we'll have n, and that'll be minus 9 plus 8. So n can be 9 or n can minus 8. Now, n has to be positive, so n must be 9. Therefore, n equals 9 because it's a positive integer. Let's do another one. When 2 plus kx to the power 8 is expanded, the coefficients of x to the power 5 are the coefficient of x to the power 5 is 4 times x to the power 4. Given k is greater than 0, find k. So the term for x to the power 5 is 8, choose 5. Now we've got a term here and a term here, so it's going to be 2 to the 3, because 8 take away 5 is 3. Then we've got kx to the power 5, which is 448 k to the power 5, x to the power 5. Now we're going to do the term that is x to the 4. So we've got 8, choose 4, so that's going to be 2. Now 8 minus 4 is 4, kx to the power 4. Plug in this bit into your calculator and find out what it is. We get 1120 k to the power 4, x to the power 4. Now, the coefficients, that's my coefficient, of x to the 5th is, I think we first went to twice, is 2 times the coefficient of x to the 4. So 448 k to the 5 must be 2 times 1120 k to the 4. So that gives us 448 k to the 5th minus 2240 k to the 4th equals 0. So now we're going to factorise this. 448 k to the 4th is k, so that's k to the 5th, minus 5 equals 0. So k is either going to be 0 or k equals 5. Therefore, k equals 5 is the positive integer. So it must be this. This is the result here. I'm going to I want a couple that's a bit more tricky, and we're going to have a little trick here for you to tuck away and remember. First, we'll look at this two-part question. So obtain the first 3 terms in the expansion 2 minus x 1 plus 2x to the power 9. Then use your answer to estimate the value of 1.99 times 1.02 to the power 9. So let's do the first bit first. So we've got 2 minus x, and it's 1 plus 2x to the power 9. So what we're going to do is we're going to take this bit out, and we're going to just let it sit there and deal with this bit on its own. And so let's expand this bit. So we'll have 9 choose 0, and then plus 9 choose 1, and that'll be 2x per 1 plus 9 choose 2, 2x squared plus, and that's, we only want the first 3 terms. So we've got 2 minus x, and then plugging these into our calculator we get 1 plus 18x plus 144x squared plus. Now we're going to do this in 2 parts. We're going to have 1 plus 18x plus 144x squared plus, and then we'll have minus x, and then 1 plus 18x plus 144x squared plus. And now if we expand the brackets and collect our terms, we get 2 plus 35x plus 270x squared plus. Now, if you think here, when you multiply this you get an x cubed term, but we only want the first 3 terms, so this is the first 3 terms, so we can disregard our minus 144x cubed that we're going to get. So that's That's the first question. Now the second question. Use your answer to estimate, so that's important. You're not going to get a precise value, the value of this. So let's look at this. 1.99 times 1.02 to the power 9. So let's consider this little trick. Let us think 2 minus x, so let's make 2 minus x equal to 1.99. So think about in the first part of the question, 2.19 here. So if we take this and equate it to this, we can think of a value for x. So x would be equal to 0.01. So let's so we've got 2 minus x, 1 plus 2x to the power 9, and we know that's equal to 2 plus 35x plus 270x squared plus something else. Now if we let x equal to 0.01, then we can get an estimation for this 1.99 times 1.02 raised to the power 9. So we're going to have 2 plus 35 times 0.01 plus 270 times 0.001 squared. Now because it's such a small number, once you start squaring it and cubing it and so forth, that term is going to get smaller and smaller, so that's why our estimate works, because x is so small. So if we work this out, we get the value, an estimate for this as 2.377. Now when we looked at how to calculate n choose r, it was a bit messy looking, but we can tighten this up, but we need to introduce a new concept, and it's called factorial notation. Now factorial notation pops up everywhere, and you'll start to see it quite often in your maths from now on. So let's think about an example of what this means. This exclamation mark is 6 factorial. So this exclamation mark in maths is not an exclamation mark, it is the factorial symbol. So 6 factorial means 6 times 5 times 4 times 3 times 2 times 1. And we say it's called 6 factorial. And you have a factorial button on your calculator. If you look for your exclamation mark on your calculator, it enables you to do 6 factorial. So in fact, n factorial is n times n minus 1 times n minus 2 times n minus 3 times all the way down to 3, 2, 1. So that means we can rewrite n choose r as n factorial r factorial n minus r factorial. And so let's look at some examples for using this. 8 choose r becomes 8 factorial, 4 factorial, 8 minus 4 factorial, which is 8 factorial, over 4 factorial, 4 factorial, which is 70. And 9, 3 becomes 9 factorial, 3 factorial, 9 minus 3 factorial, 3, and that is 6 factorial, which is 84. This is something to memorise, and this pops up not just in binomial theorem. So yeah. So last example, we're going to find the term independent of x in the expansion of x plus 5 over x squared to the power 9. So let's start working away at this, and we're thinking, when will the x's cancel out? So we've got 9, 0, and that's going to be x to the power 9, plus 9, 1, x is going to be to the power 8, and then we're going to have 5 over x squared, or x to the 4, not squared, raised to the power 1, then 9 to x to the power 7, 5 x to the power 4 squared. Now look here, x to the power 4 raised to the power 2 is going to be x to the power 6, sorry, and we want 7. So let's think about our next term. 9, 3, we've got x to the power 6, then 5 over x to the power 5 squared. This is 5 x to the power 6, but this is going to be over, this x is going to come to the power 6 also. So let's look at this term here. So we will have 9 choose 3 power 6, and then we'll have 25 over x to power 6. So these are going to cancel. So working this out, we'll get 10,500. Must be the term which is independent of x. So I hope that helps.